ultraviolet characteristics.
Okay, thank you. So my talk, do I need to do something to bring up my slides? Okay. Is a little on a slightly different topic than we've been talking about. It's related to space weathering, but it's more focused on hydration that's related to space weathering. And we'll be talking about LRO lamp results. And I presented some similar results a couple of days ago when there was a hole in the schedule. So those of you who heard that talk hopefully can still take away something from this one. Okay, so I'll be talking about diurnal hydration variations as measured by LAMP in Mare versus Highlands regions. And we see asymmetries in the distribution before and after noon, and also in and out of the magnetotail, which helps us understand, start to understand sources of the hydration. Now, of importance here is that a lot of the hydration and water and OH results that a lot of us are familiar with come from infrared measurements that sense well into the regolith. And this is my little cartoon of the uppermost part of the regolith, known as the epiregolith. So these are representative of the irregular lunar grains that are, approximately 10 microns in size, and they are fluffy and rough and irregularly shaped. LAMP senses in the far UV, and so not very deep into the regolith at all. Matter of fact, not very deeply into the top layer of grains themselves. So an instrument like M cubed is going to sense several grain depths into the regolith, probably, whereas LAMP is only sensing the top grains of the regolith. And this is important because for the temperature regime in particular, because these grains that LAMP is sensing are exposed to space. And so they don't get any conduction, or very little conduction, from the grains below, and no conduction from any grains above. And as a matter of fact, they are radiating a lot of their heat to space, and so they're in a different temperature regime. So perhaps this has effects on the hydration signature that LAMP is sensing. Okay, LAMP senses hydration because there's a very strong water-ice absorption edge in LAMP's spectral regime. This is 110 to 200 nanometers, and there's this water-ice absorption edge at 165 nanometers or thereabouts. The absorption edge location depends a little bit on grain size. We don't know, because of a lack of lab measurements, about whether OH itself absorbs here, but we think there's a good chance that it does. And so it isn't exactly clear whether LAMP senses OH or H2O, but we certainly sense a diurnal variation, as I'll show you. Thermal emission is not an issue at these wavelengths. And I'll get back to the OH versus H2O throughout the talk. Okay, but the point here is that this is a very strong absorption edge. It's actually stronger than the 3 micron absorption. So LAMP is potentially really capable of sensing just small amounts of hydration. Okay, and our models of hydration are shown here, where the spectral reflectance of different parts of the lunar surface are spectrally blue, like we just heard about a spectrally blue spectrum where the spectrum increases towards shorter wavelengths. This is in the far UV. This is 130 to 200 nanometers. So plain old lunar spectrum looks about like this, but if you add in a little bit of water and presumably OH, you're going to get a little bump up over that 165 nanometer region. And if you add in a little bit more, you'll get a stronger bump up. And the spectral difference only occurs over a very confined wavelength regime here. And you do not get spectral slope changes at shorter wavelengths or at longer wavelengths. So the way that we've been analyzing the data is to study the spectral slopes over this very small wavelength range of 164 to 173 nanometers. We measure the spectral slope there and look for changes across the surface and throughout the day. At longer wavelengths, we also measure the spectral slope to compare with and see if we're seeing the same thing or if we're not. And as a matter of fact, we do see differences between the spectral slopes that we measure at these longer wavelengths and here. And we don't see diurnal variations at longer wavelengths, but we do at these wavelengths here. And those diurnal variations are shown here. This is a big jumble of points because it's like all of the data that we have so far, at least through 2013. But the different colors are in different latitude bands. And the x-axis here is beta angle, but it's the same as time of day because negative beta angles here are in the morning, then we go through noon, and positive beta angles here refer to dusk or afternoon. And so we see redder slopes, higher values on this plot, which is consistent with more hydration from the models I just showed you, early in the day and late in the day. And then we see lower values here, which is consistent with bluer slopes or less hydration towards midday and at lower latitudes. Okay, so this diurnal variation here is consistent with changing hydration levels in different latitude bands throughout the day. And I just show this plot because we published these same results a few years ago using a more limited LAMP data set. And now we continue to add more and more data in as we accumulate it, and we're just filling in gaps in spatial and temporal coverage. So we're continuing to work on this. But now that we have more and more data, we can start to look at specific regions on the surface and see how hydration levels might be changing. And here's an example of that, where we can take a big highlands region here in the red box and compare it to a big mare region and see whether there's differences throughout the day, and we do see differences. The red points here are the highlands region, and the blue points here are the mare region, and we see that characteristic diurnal change where the slopes drop out at midday and then come back up. We see that same trend in both regions, but we see overall higher slopes in the highlands than in the mare region. And this we think could be consistent with M cubed, et cetera, results that found, I believe, greater hydration levels in highlands versus mare regions. Also, some lab results with Apollo samples of a highlands sample versus a mare sample have shown that, and these are from Poston et al., have shown that highland samples and orthositic material seems to be more able to get hydrated and stay hydrated than basaltic mare material. So this seems consistent with the results that LAMP is getting. Oh, and I wanted to also show you that, yes, there are compositional differences between these two, and could that be related to these overall slope differences that we see? And we do not think so, because if you look at the blue line here, which is standard mature highlands region spectrum, reflectance spectrum, compared to the cyan one, which is a standard mature mare region, we see definite differences in those reflectance spectra at longer LAMP wavelengths. But in the water absorption region here, over that very small wavelength region, we don't see big changes. So we think that this difference here is due to hydration levels rather than to inherent composition. Okay. The other thing, this is the same plot, but I want to focus now on this shape here, this distribution. As you approach noon, in both regions here, it's especially obvious in the highlands, that you get kind of a sharp drop-off as you approach noon. And then it's slow at noon, and then it more slowly ramps back up. So this is an asymmetric distribution. And we think that this could be related to the movement of the hydrating molecules around the surface during the day, whereas where they seem to maybe want to hang in there until the temperatures get high enough that they want to desorb and leave. And then later on in the afternoon, as the surface cools off, they come back and populate the in between the grains there and adsorb onto the grains, presumably. Okay. And we see, let me come back to that. We do see this trend in other regions too, but I don't think I'm going to show that to you. But this seems to be a trend across the surface. Okay. The other thing that I want to show you is this same mare region that we looked at, which is on the near side. So this is actually spends a lot of its time in the magnetotail. As the moon passes through the magnetotail, this is the region that's going to experience lower amounts of solar wind protons. And so we thought, well, if we're seeing solar wind produced hydration, should we see a difference when the moon is in the magnetotail and not getting those protons? And so here in the red are the points during the whole mission so far of this region here. And so you see that same distribution there. And then the black points are the subset of the same data set, but when the moon is in the magnetotail. And we expected that if we're seeing the prompt production of hydration, that we might see that while the moon is in the magnetotail, the black points cover the lower red points, for instance, lower hydration levels. And what we find is that we don't see that. We don't see that there's a big difference between in the solar wind and in the magnetotail for this region here. So this can help perhaps place a constraint on the hydration, at least that LAMP senses. And I know that Tom Orlando and Darby Dyer have been talking about solar wind not being able to produce water anyway, H2O, at the moon temperatures. So perhaps this is related to that if LAMP is indeed sensing H2O anyway. Here's another example of this where we look at this region here. These are smaller regions, so there's fewer data points, but this is a highlands region compared to another highlands region of the same size and same latitude band. This is one that's always in the solar wind, and this is one that is sometimes in the magnetotail. And we do not see big differences between those two with this limited data set anyway. But for these points that while they are in the magnetotail, they're black here, and we don't see that they are populating like the lower points on the plot at all. So I'll conclude here to point out that there's a lot of data here, and there's, we're continuing to add more data. And we see compositional differences in the amount of hydration. We do see this diurnal variation, and we see it changing around noon, which is telling us that perhaps we are sensing not hydration that's promptly produced by solar wind, but hydration that is moving around on the surface. It's diffusing and bouncing and perhaps diffusing, but certainly migrating around on the surface. And the really good test here that we've been talking about doing, and that maybe ties it back to the solar or to the space weathering that's more being discussed here, is, and this seems to have cut off here, but I'll say it, is to look in the swirls. Because if the swirls should not be immune to migrating OH or H2O molecules, and yet I know that at longer wavelengths, swirls are areas of a lack of hydration. So if LAMP also senses the lack of hydration there, then that tells us something about how much hydration we're measuring diffusing. Or maybe it could say something about whether LAMP is measuring a different population of hydration than, say, M cubed. So I'll leave it there. Thank you.
Thanks, Amanda. Do we have any quick questions about this? And remember, after our last talk, we'll have about 10 minutes probably for discussion about all the talks we've had during the session and any other things that are relevant from other sessions. One question.
Okay, Amanda, I did appreciate in past presentations that the symmetry of the hydration between sunrise and sunset, basically. You show a rapid increasing, a decrease in the hydration before noon and a slow increase afterwards. Yeah. But it's interesting to know that the level of hydration is almost the same at the terminator. So we expect to see a higher concentration soon after dawn than before dusk.
Yeah, and we don't see that so far. Now, the observations, as you know, at the higher beta angles, we have fewer observations right now. So as we continue to improve our statistics, maybe we can say more certainly what's happening right at dawn and right at dusk. But we did expect to see a difference, and what we think, if we're not, we think that could mean that we're just kind of sensing some type of saturation. Like we can only sense so many hydrating molecules at that super top surface, and then that's it. So that's
and second quick question
okay.
is the same method being plausible for OH?
For OH?
Yeah.
That's what we are assuming here.
Okay.
Yeah.
Thanks.
Thanks.